The last section that we're going to be looking at here in section 9.7 are the different types of polar graphs, and we'll do some investigations of these. If you go to your textbook, you will see there's a whole library of different types of polar graphs, but we're going to focus on two types in this section. One is the limicons, the other are the rose curves. And the first we're going to start off with are the limicons. And the limicons are in the format r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. So you can see right here, this is going to be the format for the limicons. There's that plus or minus in between the constant and the trig function. And both of these are having a is greater than 0. So there's four different types that we can get: an inner loop, a cardioid, a dimpled, and a convex. And the way these four types of limicons look are based off of the relationship of A and B. So the first criteria where I get an inner loop on this limicon is where A divided by B is less than 1. In other words, A has to be less than B. If A divided by B is going to be less than 1, that means B has to be the larger number, so I get a fractional piece. So if I'm going to follow the format r equals a plus or minus b, let's just go with the sine of thetas for this one. My A has to be less than B. So one that would work would be 2 plus or minus 4 sine theta, would be something that would create an inner loop. R equals 1 plus or minus 2 sine theta. Once again, A is 1, B is 2, so that would create a value that's less than 1 if I divide the 2. Or I could say R equals 2 minus 3 sine theta. Plus or minus sine theta, it really doesn't matter. But once again, A is going to be 2, B is going to be 3, so that's 2/3. And depending on what values you use, you're going to see an inner loop form. And what I mean by an inner loop is something like this is going to form. That guy right there is the inner loop. So let's pull out our calculator and let's look at one example of that. Let's just go 2 plus 3 sine of theta. I'm zoomed in a little too much there. Let me zoom out slightly. And there I'm zoomed out a little too much. So we'll zoom back in. I guess you won't see the whole picture there. But there's what an inner loop looks like. You can see right there we've got that inner loop, and this is a big circular pattern. So that's a limicon that has got an inner loop. The second is a cardioid. And a cardioid has A equal to B. So if I'm going to follow the format r equals a plus or minus b sine of theta, if A divided by B is equal to 1, we have to have the relationship that A is equal to B. So r equals 2 plus or minus 2 sine theta. R equals 3 plus or minus 3 sine theta. I mean, really whatever you want. R equals 5 plus or minus 5 sine theta. Wherever your A and B are the same, you're going to get a cardioid. And a cardioid looks like a heart. So for this one, let's try 2 plus 2 sine theta. Once again, I'm zoomed in too much, so let me see if I can zoom out and get a better picture. Okay. There you go. That sort of looks like a heart, an upside down heart. But if I were to follow this around, this curve up here is connected, and that looks like a heart. So the idea with a cardioid is when I draw it, it's going to look more heart-shaped. The third one is the dimpled, where 1 is less than A divided by B, which is less than 2, which is saying that my fraction has to be greater than 1, but less than 2. So an example of that would be 2 plus 1.5 sine theta, or 3.25 plus 3 sine theta, where A is slightly larger than B. If you get too large, if you get more than twice the size of it, then you're going to be larger than 2. So this number in front can't be double what B is. And if you have a dimpled lemicon, it sort of looks like a cardioid, but it's just a little dimple. It's not quite as sharp. So it'd be something more like that you got. Yeah, a little dimple right there. Not as pronounced as with the cardioid. So I'll let you plug that one in and see it for yourself. The last one is the convex, and the convex pretty much looks like a circle with a flat side to it. And this is where A divided by B is greater than 2. So that would be something like 4.1 plus 2 sine of theta. And if I graph that, I'll have something a little bit flatter right there. And once again, I'll let you confirm that by plugging it into your calculator. So what happens to the loop as your values change within a single column? Well, your size gets bigger or smaller. And you saw that on my graph where some of them were too large to fit in the window. The whole graph gets bigger and smaller. And then specifically, the features are more pronounced. Meaning, if I look at my inner loop, I can see the inner loop more clearly. Or the cardioid, the curve where it comes and meets as a heart, is going to be more clear. Do any of these graphs have a type of symmetry? And if so, can you describe it? With all these, you can say, yes, there is some symmetry, and it's around the line theta is equal to pi over 2. That's what we used to call the y-axis. All these are symmetrical around that y-axis. And is there any difference when you change the sine to cosines? If I were to change all these sines to cosines, you're going to see that there's a 90-degree rotation. So instead of me being around the pi over 2 line, or the y-axis, you're now going to be symmetrical around the polar axis. And the polar axis is this line here. So if I were to change this sine to cosine, my curve would now be on the side. Or this cardioid, the heart shape would be on the side. So the reflection would be around this x-axis, which we call the polar axis when we're in polar coordinates.